We have more time to go slowly to show some, say some details, but I don't want to show details, but just to have a compact picture of what we are to, about the goal of this methodology. So I would like to restart with some of the equations that we introduced the last time in order to show how, very quickly, but very simply, how we can get from this system of equation we can get this convolution integral that is at the very basis of our developments. So we have the first equation of this set, that is the equation that we are write down to monitor our master particle. This is X is for the master particle. But we have an interaction with the other particles of the system that is represented by this linear combination that is represented in terms of all the coordinates of the remaining part of the system. And of course, you have a set of equations in which you can represent the dynamics of the remaining part of the system that is, of course, affected by the presence of the particle by this x here. So x flex is the dynamics of the hidden part of the system. So our aim is to eliminate from this equation x flex in order to get the basic equation for our analysis. And this can be made readily, actually, but just because it is a simple procedure, it helps to follow it in order to understand that our starting equation is pretty simple and does not contain any kind of mathematical trickery. So we have an equation that is very easily represented this way. I rewrite this. And this is for the master. And then we have a second equation in terms of the flux variables. What is it? Okay, and this is for the hidden part. So the starting point is very simple. So we start from a linear description of our system, and then we want to derive a simple property for the master equation. The simple property is represented by this kind of substitution. So actually our principal goal is to derive from this equation, from the first one, an equation like that, where you have a damping effect, that is an actual damping effect. So if you are just monitoring the first equation, it amounts definitely to a dissipation effect, but plus an epsilon function. That means that you are introducing something that we have to discuss, because in the procedure that will lead us to derive this equation, we take into account some kind of hypothesis that must be suitably discussed in order to understand what are the limits and if we have to respect some special conditions in order just to write down an equation that contains only the dissipation part. So if we are in the position of neglecting this epsilon function. So actually we can transform everything in the Laplace domain, and so you can get this simple equation. Capital is for Laplace transform. Then we can transform the second one. Then you can solve the second set just in the obvious way. So you can collect the terms containing dynamic information about the system. Then you have to multiply times x flex. And then you have on the right-hand side just this term here. Then you can get a solution for this that is simply expressed this way. So if we invert this matrix and we call this matrix G, so we get this very easy way to represent the solution. Well, this is the solution for the set of hidden variables. Of course, they depend on the x variable, that is the master variable. So this is true if you consider in this case that all the initial conditions are set to 0, meaning that for the hidden variables you are assuming that at the time t0 this is the 0 vector, and of course even for the velocity at the 0 time is set to 0. So this is the solution. Just in case you want to include the effect of initial conditions, you have just to add a term that again depends on the spectral properties of the operator related to M and key flex. But this is not the case, but we can do really to get this result. So we can insert this expression directly into this equation. Before to proceed, we have just to observe that the G matrix contains information about the dynamic of the system in terms of M and key flex, meaning that you can write easily this matrix in terms of eigenvectors matrix and the lambda matrix that are eigenvectors and eigenvalues related to the hidden problem. So in particular, this is useful for the following. This lambda matrix is a diagonal matrix and contains information about the natural frequencies of our environment. So actually the picture that we have is that there is an oscillator. This oscillator is attached to a complex system that is the environment. And then if you consider all in the environment without the presence of the test particle, what we get is it is described by a lambda matrix and an eigenvector matrix that contain the spectral properties of the environment. So our main point will be in the following about the distribution of those frequencies. So omega n1, omega nn. Okay? Then if you go to plug this expression into the first equation, you can get a nice result. Because at this point we don't want to see this equation anymore, and we can simply get this expression here. Here you have this expression for x flex, that is simply the G matrix. Then you have, we want to separate the contribution, so I take the contribution in terms of x on the left hand side, so meaning that I want to put it here, then I have x here, and then on the right hand side I have simply the force directly applied to the oscillator, meaning that there is a force directly applied here, that is F0. Then indeed you have in general a set of forces that are applied to the environment, and this set of forces Flex. So the second contribution coming from the effect on the motion of this particle because of the application of these forces is readily evaluated this way. So you have to consider in this case the contribution of K0 flex transposed then you have again G, and then you have F flex. Okay, so this is the picture we have for this problem. If you consider now the inverse transform of this equation, so we can get the solution, the equation in terms of time, and then we can return to the time domain just considering this. So I know that K0 flex and K0 flex is a constant vector, while this is depending on the Laplace variable S. This is depending on the Laplace variable S. So actually here I have a linear combination of products of this Laplace transform and this Laplace transform. So when I get back to the time domain, I have just the convolution of them. So what I can put here is just this equation. So you get something that is integral of the inverse transform of this guy, that is G, say. Then you have this one, and then you have the x variable. Then you have to integrate in time domain, and then you have here again something that is multiplication times this vector. And then you have here F0 plus something here that depends on this transform. Suppose that we neglect this term because it is not actually the main point of our analysis. So actually this is the picture of the problem that we have. And then all the considerations that we can introduce are exactly about the nature of this term. So this is an exact result. So actually this can be applied to any kind of linear system without any kind of special hypothesis or special simplifications. So this is actually a rather general expression. That is just the second equation that we have on the screen. So what is the point?
Small g
is the inverse transform of G omega.
You interpret x and k0 shouldn't have no, right?
Shouldn't have?
You see in your notes, k0 is inside.
Oh well, it's just
Yeah, because it's a matrix, right? So
yeah, it's a matrix.
apply to x.
No, it is not applied to x. So here you have a matrix, and you are convolving each element of the matrix times x.
But before you had k0x, it's just a detail.
Oh, this is not k0x. It is
No, on top, line on top.
here.
Yeah, you have k0x. So why is the k0 outside?
Oh, because it's constant.
Yeah, but no, it's an algebraic thing. K0 and x are not of the same dimension. If k0 is a matrix,
But it is a scalar. This quantity is scalar.
k transpose g k0 is not.
So G k0,
Oh, sorry.
or maybe that it is a vector. This is a matrix. This is a vector, and then this is a transpose vector, and then it is a scalar. Okay. So and the same here. So you can put, it is up to you if you prefer to, well, but there is a difference in just in the sense that you can compute, okay, the metrics, or, but since they are not depending on time, then you can push them out of the integral. So what is the main point now? So we want to understand something else about the property of this convolution integral. And the step forward that we are actually doing does not involve, again, any kind of approximation. So we want just for the following, we want just to expand the expression for this kernel. So we have a kernel here in time, and this is in frequency domain. We want just to express this kernel using the Padé approximation, meaning just that we want to make explicit the dependency of the G function on the spectral properties contained into the eigenvalues matrix. So what we have to do is just to plug into this Fourier transform equation just the expression for G. There is nothing else that's an expansion in terms of a series of ratios. Then you have just to put it inside, and now it is just easy to recover the time domain form of this equation. So it is just an easy trick. I re-express G in terms of this expansion, then we can get the time domain form for this equation. That is perfectly equivalent to this expression, except the fact that in this form we are more close to our final goal. So the main point is that now we have a quite simple expression for this kernel. Then ht is the Heaviside function, st is a summation of harmonic functions, and then you can get the expression, an explicit expression, or more explicit than in the case before.
You have an estimate of which is the error you are introducing once you replace the true G with its Padé expansion?
Well, the Padé expansion is not an approximation in this case. Generally, the Padé expansion is an approximation if you are looking at infinite dimensional systems. And then you are trying to expand the green function just using a finite number of terms. Okay? It is exact. It is exact, and but your remark is useful for the following. So we are going to do exactly the inverse. We are trying to emulate or to transform a finite dimensional system into an infinite dimensional system. And the reason is quite clear. It is much more complicated to deal with a finite dimensional system than to deal as a continuum function. I would like just to give you an idea why it is complicated to deal with this kind of term. So you have a number of discrete eigenvalues. This is the real nature of the spectral properties. Now if you go to plot what is the behavior of the elements of this G function, it's easy to understand that if you plot, for example, it is G H key of omega in terms of omega, then you have here omega n1, omega n2, and so on. So for each of these eigenfrequencies, you have singularities for this guy. So this is a quite difficult property that is exhibited by this G function. The reflex of this complication that you have here in terms of this resonance peak that you have just in this function is just the representation of this function using a series. Because you have a discrete set of eigenvalues, that means that it has discrete spectral properties, and this is a problem. So our step forward now is to introduce a different approach here, at the moment without introducing any kind of error, but we can look at this term and we can say this term can be expressed by an associated integral like this. We can introduce a dummy variable that is psi. Then we can try to express the relationship between the summation, discrete summation, and integral. And then we can replace the summation introducing the integral and a remainder term. So it is very obvious that we can express the integral through a summation plus a remainder term. Of course, as we know from elemental mathematics, so what we can say about the remainder term is something, but of course we have not a complete information about R the t, because of course it is like, for example, in numerical integration, you can express an integral considering just a serial expansion, and then what you can get from some expression for the remainder term are some upper bound or lower bound related to the error that you are introducing in this kind of approximation. But at the moment we supposed to use this expression, and then we have to use the remainder term in order to not modify the equation that we are writing. So if you just substitute this expression, instead of s, we introduce I, but also the remainder term, the situation is a little bit different with respect to the previous case, just because of the addition of a second term, but nothing else is happening. So the real point is this. This is, again, an exact and general result for linear system. So we have a first contribution that is here, in which summation has been replaced by an integral, and then you have introduced something that is an error with respect to this representation, and this is the integral that you have here. Just a physical remark. What is the meaning about this function? You can see that in this case you have a discrete spectrum of eigenvalues. If you are taking this integral, this function omega xi is giving you a continuous distribution of eigenvalues. So actually what we are doing physically with this replacement is treating the environment that we are coupling to our elemental oscillator has an infinite system, while it is actually a finite system. This is the real replacement. I would like to just to remind you the example that we analyzed yesterday. So the case of a piston that is interacting with an acoustic waveguide. So suppose that this is the example that we are using, in which we have the boundary here. So this is a finite length pipe. Of course, in this case, this is just a one-dimensional problem of wave propagation. Then here you can extract a set of natural frequencies. But this is a discrete spectrum of natural frequencies. Now, if you look at the spectrum of these natural frequencies, so if you analyze the number n and the number n plus 1 eigenfrequencies, you have something that is a frequency interval separating the two that depends on the inverse is proportional to the inverse of the length of the waveguide. It's easy to show this result. Now, if you increase the length of this pipe, what you get is that the mutual distance between the eigenvalues is reduced. The more the length, the smaller is the gap between frequencies. So if you have an infinite length for this pipe, the result is that you have not a discrete spectrum of eigenvalues, but just a continuous distribution of them. So actually, in this mathematical trick, what I'm doing is actually a modification, but a quite deep modification of the nature of our system. So we are trying to emulate a finite dimensional system by using a finite set of oscillators. So this is what is at the basis, that form the basis for this analysis. And clearly, the effect of the term RT is very important, because it takes into account what is the real effect of having the system finite, because of the presence of a boundary. Of course, we don't see a boundary in the case of a general system of particles, but the interpretation that we can give is exactly this way. So the system is finite, meaning that in this kind of analogy, the pipe has a finite length. Okay? So the analysis of RT is very important. So we can develop for this guy, we can develop an explicit expression, and this is very nice, because now this is actually something that represents, as you can see here.
Sorry, what's F bracket A?
What is it? Fourier transform. It's the Fourier transform of this kernel. So this is the convolution between x and step function multiplied by the integral.
So you calculate the Fourier transform of this convolution?
No, just of the kernel.
Just
Okay. So the kernel reveals that you have an imaginary part and the real part. So the imaginary part is just the responsible for the dissipation effect that you observe in the motion of our oscillator. Why this part? Well, this part is just something that represents a reactive term. So, just going to simplify. I can express, for example, but just to have a more easy expression for our consideration, but it does not affect the generality of the approach. Suppose that you want to approximate this Fourier transform just considering what we call a narrow band process. So suppose that you have that the frequencies of the environment are close to a given frequency that is omega 0. So suppose that all the set of frequencies are located in a relatively narrow band, and then you have some reference frequency that is omega 0. Okay? Then what you get from this result is that you can use an approximation for this inverse transform, and then you can get, starting from this approximation, the final equation that you have in time domain, where you have an actual dissipation term, then there is the reactive term that is just an elastic force, plus the presence of this epsilon element. So actually we have to discuss the remainder term. What it does represent actually? It represents the presence of Hikos in the system. So even a finite system of oscillator, for the reason that we are discussing, can exhibit an echo phenomena. So it is an energy re-injection into the master. So we are releasing energy from our master oscillator to the environment, but it will maybe that after a certain time the energy comes back to the principal oscillator. It's just the case of this instructive example. You have energy that is traveling towards the boundary, then you have reflection from the boundary, and then you can get again the energy at the master oscillator. Of course, these terms can, at a certain time, introduce an analogous term like that is with negative coefficient, so amounting again to an injection of energy into our system. So, of course, the presence of this term, that is a dissipative term, in this equation can be established only if we can say something about the presence of this epsilon term. In that form, so we can quite easily discuss some properties for this reminder term that I would like to show you. So the main result. So I don't show any kind of details, but just to give what is the basic way of reasoning for this. So the main result is that for t that is smaller of the time t star that we call the return time, the contribution of epsilon is negligible, meaning that this equation that represents a phenomenon of dissipation is actually a good way to look at the problem, but just up to the time t star. T star is named return time and depends on the form of the Kernel Gestalt, meaning that depends on the spectral properties of the environment. So our aim is just to establish possibly an expression for T star. That's it. So since the integral and the summation are easily related by the reminder term that can be recovered by simple analysis, so we have just to introduce two simple lemma. The first property is that if you have are considering the integral I, it has a quite nice property. So the integral that we replace it in the expression to the sum has the property that for t that tends to infinite, this integral et vanishes. This is an important property. This means that from the following, from the previous analogy, it, the integral, is just the impulse response of the environment. So if the impulse response of the environment goes to 0 as t tends to infinite, again it means that you are thinking to an infinite system. So for this reason it has this property. And this property can be easily demonstrated by using this lemma. And it's very easy to show that if the distribution, the spectral distribution of eigenfrequencies, so if it is psi, it is 1, it is 0, then you have a distribution of eigenfrequencies, omega psi. For any kind of distributions in which you have the derivative of this distribution that is different from 0 for any psi belonging to the interval 0, 1, you have that this is the syntactic expansion of this integral, meaning that the principal contribution goes to 0 as 1 over t. If you have somewhere some points in which you have that derivative goes to 0, in this case again it goes to 0 but with a different power of t. So the final result is that in any case we have that the integral goes to 0. So this is the main point, and this means that for large t the summation has the same order of magnitude of the reminder term. Then there is a second property that is based on the usual expression for the reminder term when you are using numerical integration. That means nothing else that for t close to 0, you have that the summation is just equal to the integral. On the basis of these two properties, we can conclude that at early times, S is close to I. At large time, S is close to the reminder term. And this is a useful property to compute or to give an order of magnitude of the return time. So the situation is more or less this. If you represent the integral as a function of time, what you get is something like that. And it goes to 0, and is predicted by this property. If you consider St, you have that St is close to it at early time. Then you have something that is a little bit different. At a certain point, you have a jump of S. So this is the function St, and this is the function it. So they are very close for a small time, but after a while, St is apart from I in a very significant manner. This is the effect of equals for the finite system. So we want to estimate the return time, meaning that you want to estimate what is this characteristic time duration, time interval. So there is a quite simple analysis that we can do in order to evaluate what is this time delay. The first step is we want just to compute what is the first peak for S and I close to t, close to 0. So we are just going to evaluate what is the peak value for these two functions. We call this t first peak. Then we can evaluate both the time t first peak and the amplitude for these two functions. Then what we can evaluate is what is the time that we have to wait in order to see the function S to gain again this amplitude. And this gives us the time duration of this interval. So the first problem is find the first peak. So find the first peak, we have just to find what is the first time at which the derivative of S goes to 0. It's difficult to do this kind of analysis without using I, so we use I because it is at early times, and this approximation is allowed. So we can find from this equation the time that corresponds to the first peak. At late times, we say that the amplitude that we have at the first peak is equal to the amplitude of S at the return time. And then, again, we use the fact that this S at the first peak is equal to the integral, that is easier to evaluate, and S is at the return time can be evaluated by the remainder term, that is, again, easier to evaluate. The final result is that we can find an upper bound for the return time. And its expression is quite simple. So it depends on the number of particles that you have in your environment. That is proportional to the equivalent damping that you have in your equation, and to the equivalent stiffness that you have in your equation, where C equivalent and K equivalent are exactly the terms that come from the interaction with the environment. So say that the final...
But you don't have any lower bound.
You have not?
Any lower bound for T.
No.
So you know it is more or less close to
Yeah, more or less. More or less. So in numerical simulation, give you a good feeling that it is generally very close to the time that these phenomena show up. So this is the final picture. So this is the equation of motion of our system. This equation is valid only with T that is less than this quantity, and the equivalent damping and the equivalent stiffness can be evaluated in terms of global properties of our environment. So this very simple function is just the distribution of eigenfrequencies in the interval that you are considering. So it is a global property, say, of the collective motion of the environment. So what you can estimate, and the only thing that you need to estimate for this is having a function that describes, this is the n over the omega, that describes the problem in this way. If you give an interval here, that is the omega, then you have represented by this area the number of eigenvalues n that are contained into this interval. So this is the actual description that you have of the environment. So with the number of degrees of freedom that you have, and with this descriptor of a spectral property of the environment, you can estimate the radon time. And then you have also an estimation of C equivalent and K equivalent. So this is the final picture of our problem. I would like just to go back to this kind of example. So it appears, even it is at this point an approximated formulation, it appears that in some particular conditions, even if n is finite, we maybe that can get an upper bound that is infinite for the radon time. So we can control actually the radon time from our environment just playing with this function. So it means that if this function has a very large value, even with a sufficiently small number of oscillator, you have a radon time, so reflection of waves, that are delayed of a large amount of time. Theoretically, you can select functions for which this term goes to infinity, and then you can get from your waveguide something that is a equals-less effect. It is really possible, this, and what is in this example that we consider for the pipe the main point. The main point is that if you consider again this example, you have not to consider, so if you modify the spectral properties of your environment, you are not just considering the simple case in which you have just, say, D'Alembert waves into the waveguide. But special selection of this function can lead to have dispersive waves into the waveguide. So dispersive waves are characterized by the fact that if you put here an impulse of energy, and if this impulse of energy is sufficiently narrow band, that is just the hypothesis that we made about our system, so this peak of energy translates along the waveguide with a group velocity that can be determined by the characteristic properties of the waveguide. Now you can establish in this analogy that this guy is eventually the inverse of the group velocity that you have here. So actually, when you have that this term goes to infinite, it means that the group velocity in this waveguide goes to 0. So that I can build up a waveguide that, even if it is finite, has particular properties in terms of propagation of energy. So we can produce by the same theory, so we published some paper about that, just using the same theory, you can produce a wave stopping phenomenon. So you can put some energy here, and then you can see just selecting properly the waveguide, that the energy is going here and then it is stopped. So you have a sort of phenomenon of localization of energy, but the energy remains at the same section, except, because this is not an exact result, except that you have some part of the energy that is flowing, but a small amount that is flowing towards the end of the pipe. Then you have some reflection of this small amount, and then you have very small echoes. So what you actually have at this section is that you have the first pulse of energy, then you have very small echoes here, like this. But the main part of the energy remains trapped into the waveguide. We realized this system because it is not possible, of course, with a simple system like an acoustic waveguide. But we realized this kind of waveguide in a very easy way by using Euler-Bernoulli beams on Winkler foundation. So if you take, for example, the case of a simply supported beam that is on an elastic bed, then if you put here an impulse force, if the selection of these elastic bed properties, the property of the beam and the characteristic spectrum of the force that you are applied here, what you observe is that the energy is stopped before it reaches the boundaries. So it is quite intriguing problems. So the main point now is that I don't want to go to bore you much more about this, but what is the main point that we can approach now? I can ask what are the distribution of frequency. This is the key point of our analysis. So I can ask what are the distribution of frequency that makes epsilon as close as possible to 0. Because if I can design a system in which the distribution of frequency is such that this epsilon goes to 0, I am in the condition of having the maximum dissipation effect. And then we used a procedure that is a variational procedure in order to identify what is the best distribution in order to get from a finite system an infinite behavior. And this point can be solved by a variational approach, so a quadratic variational approach. So using a minimization problem, we can get an unknown from our problem that is represented exactly by this function. So this function can be the unknown of our problem, and we can set this function in order that this term can be neglected. Of course, it is possible to approach the problem and actually, in a very unexpected way, the problem has a closed form solution. So we found a closed form solution for this minimization problem. Then we built up, used this information not only for publications, but to produce devices. So the main point is that if I understand what is the best function, I can design devices that have the property to absorb energy from a given master in a very fast way and permanent way, even using a small number of oscillators. So the example that I want to show you is some applications that we made in the field of aerospace engineering in order to reduce vibration during the liftoff of rockets. So we designed part of the payload structure in rockets in order to reduce the vibration of the electronic device at liftoff. So at the beginning, when you have the rocket that is launching all the satellites that are contained in it, you have a really impressive amount of vibration when you switch on the boosters. You can imagine. So you have the switch on of the boosters, you have an enormous vibrations of the system, and of course all the electronic packages that are on board are subjected to tremendous vibrations. Now it is a very big problem for two reasons. The first reason is that these kind of vibrations can produce a damage on the electronics on board with a double problem. Which kind of electronics you have on board? You have on board the guidance system of the rocket. So if the guidance system of a rocket is out of order, of course it is a very problem even in terms of safety of the rocket itself. But we installed this kind of device in order to reduce the vibration on the electronic package mounted on board the satellites that they have to release once they are from the Earth. In that case, if you have the satellites generally have a lot of instruments on board that are used in order to perform experiments in orbit. And you pay a lot of money in order to launch these satellites in orbit. Now, if the instruments that are on board are out of order, so you are paying for nothing because you cannot receive data from the satellites. One of the big requirements for this device that you have to mount on board, and then when they switch on the boosters of the rockets, you cannot use any kind of electrical device because they can interfere with the guidance system of the rocket. So you cannot use only passive systems in order to reduce vibrations on board. And this is a good example of a passive system that we can install on board in order to reduce the vibrations of the electronic package. I will show you some results about that. What I would like to avoid in this case is to show you I don't know if okay, so I think that we can, I don't know, it's up to you. I explained it very quickly, the procedure in order to get the best distribution yesterday. But since we went over this part, maybe that I skip this part and we can just jump to some applications. So say that more or less this is the last lecture. So tomorrow is just to say goodbye, I guess, more or less. No, it is not? Okay. Okay, some words about the approach to find the minimum function. So the role of the summation. So this is the point of view about the previous problem. This is just what we are doing in order to find the best configuration for the environment, meaning that we are looking for the best distribution of eigenfrequencies on the environment. So in the set of oscillator that we attach to main resonator, that's the point. So if you look at this expression, this is exactly of the same type that we considered in the previous case. So it is just a linear combination of harmonic functions that contains the natural frequencies of the environment. What is the integral that we replace to this summation? It is just an integral like this. So it's very possible for this kind of come on, are you sleeping? You fall down. Okay. So this is an interpretation of the integral. Is just that this is the arithmetic average of some random quantities, the natural frequency of the system, and then you can get the ensemble average of the impulse response of them. So it is an interpretation actually that we can use in order to compare the impulse response, that is the summation S, and the integral. So these two terms that are S and I can be interpreted. This is just an arithmetic average of random quantities, and this is just the exact average of random quantities. So generally, when you use the evaluation, a very simple technique to evaluate what is the expected value of some quantity, is that you collect the data, then you produce the summation of this data, and then you divide for the number of terms that you observed. It's very easy. Now there is a very nice question. You obtain something that is an estimate, is just an estimate of the average, the real average, the true average, what something is called true average or exact average. Because you want to, I would like to tell you this story because it's very nice. This is a story that has been considered in 1941 by a set of people. So they are considered just a random variable, that is xi. They want to on the basis of these samples that are just random samples of a certain variable, to calculate a parameter that we can call lambda, that is just 1 over n, that is the summation I equal 1 to n of these quantities that are random quantities. This is what everybody can do in order to get what is the expected value for the variable. That's it. But did you think about this problem? Suppose that there is a probability distribution for x that generally you don't know. Generally it is unknown, generally. In order to determine this, you have to make a lot of observations. But suppose that you don't want to do this. That is actually the more frequent situation. You have just a sample. You want to give an estimate of the average, then you take this expression. Now you can put this problem and this question. If I want to exactly compute the average for x, this should be the expression that you have to use. Distribution for x, then you have x, and then you have to integrate this function. Okay? Did you think about this problem? So generally we use this to evaluate the average, but the exact average is represented by this guy. So in 1941, some people were putting the question, what is the relationship between this exact value for the average and this is just an estimation of the average? So there is a difference, of course, between the two. Of course. But really the problem is quite intriguing, because the relationship between the exact average and this quantity that is called the estimator. So this is the estimator of the average. The relationship that there is between the estimator of the average and the average itself, in the sense of the theory of probability, it's not obvious at all. So it is very difficult to discuss theoretically this problem. So they started to think that there is some element that can play a very important role in this comparison. So one could think that, well, if you take a number large enough of samples, I can get a good estimate for the exact value. This is more or less intuition. But there is something that in our intuition does not play any role. And the question from this guy was, it is really possible that Px doesn't play a role in this game? So it is really possible that independently of the choice of Px, the way this estimator represents the average is not affected by the choice of Px. In other terms, they were asking to themselves, there are a class of distributions Px that are more lucky, in the sense that if you provide the average using this estimator, you can get a quite good representative value for the exact average. And there are less lucky distribution for which this kind of comparison is poor. Well, the answer to this question came in 43 in the frame of the theory of estimators that was just born at that time. And so there is a very beautiful theorem that says that if you want to give a strict point of view about this problem, you have just to compare this one to this one. And I say, the estimator that you are using, while this is a deterministic quantity, so this is deterministic quantity, this is not. This is a random variable. In fact, the second one does not depend on the samples that you are observing. So this is just depending on the Px that you select. But if you look at this, suppose that I make 10 observations of the quantity x. Then I repeat the analysis with another set of 10 observations. And then another set of 10 observations. For each set, I can get lambda 1, lambda 2, lambda 3, and so on. Reasonably, I cannot expect that lambda 1, lambda 2, lambda 3 is always the same. It means it's a random quantity. So it is random for each set of observations. So you can say, I want to compare these two. The only strict way to compare the two is just to compare the average of lambda minus the average of x squared. What is it? It is a standard deviation of the error that is involved in estimating the average by the estimator. There is a beautiful theorem that was proved in 1943 by Kramer and Rao. This beautiful theorem states that for any kind of choice you make about Px, this quantity has a minimum bound. So there is a minimum for this variance that cannot be passed. So it is the lowest bound. So it means that if you compute this and you say that this is this square is always larger than a special function that depends on the selection of P. So this is the Kramer-Rao inequality. This guy is strictly related to the so-called entropy of the sets of data. So what happens is that if you can compare these two, you can compare, but for sure this comparison has a bottom value. And so you have something like that. You can select different distributions, but there is a minimum for this function that can be obtained just for a special selection of the distribution, P star. But this is clearly a variational problem, because this bound that is called minimum variance bound depends on the selection of the distribution. So it means actually that what you are asking in order to get the best P is that you have to select P in order that this guy just catch the minimum. So it is a problem of minimization, definitely. So what we understood in our way of looking at a problem is that we can take advantage from the theory of estimation. So we took the theory of estimation, modified the theory of estimation in order to readapt everything to the mechanical problem. And the real point is that it exists P star that makes minimum this variance, meaning that there exists a frequency distribution. This is the translation to the mechanical problem. It exists a distribution of frequency that makes your environment as close as possible to this, that is the infinite system. So a finite system can mimic as close as possible an infinite system. And this is actually the bound that we found using our analysis.
Which is this P star?
Is this. So readapting everything and demonstrating the theorem in readapting the problem. So originally they didn't use calculus of variation. They used, because it is possible in some cases, since the problem is a quadratic problem, it can be approached by linear algebra. So they used the Schwarz inequality. And they can get the bound for this. So we readapted everything and we used the calculus of...
Which is the optimal distribution?
Yeah, I would like to show you who is the... You want to look at the face of this function. It's this one. So the original problem was to find... So this is the variational problem that we want to solve. This is the problem. So we define the deviation of the sample from the average. Meaning, this is the finite system, this is the infinite system. Then you want to get the minimum for the distance. So this is the distance between a finite dimensional system and infinite dimensional system. And you want to keep the minimum for this functional. So it depends on the probability distribution P that is here and is contained, of course, here. We have some constraints for this P. Some constraints means that you have that there is a prescribed average and a prescribed closure equation. Then the problem that you have to minimize is this. Over bar means to compute this integral, so is an average. Then if you develop everything, the final Euler-Lagrange equation for this problem is this one. P contains the optimal distribution. Then from this equation, so this equation is made an identity by selecting this particular relationship. And from this it is possible to to say that there exists a family of distributions that match this minimum condition. Okay, and this is the final expression that you can, I don't know if, no. I have a final expression for this, where this function, g omega, depends only on the physical characteristics of the system that you are investigating. So, in some sense, this is the best distribution that you can take, provided that the system has a certain topology. So g omega depends on the special form mechanical properties of the system. Sorry? No, of the global system, say. Mm-hmm. Of the complete system. So it is a global property. We say a collective property of the environment.
So instant and your mass spring of both.
What is the characteristic function for g for this system? Oh, well, for this system is very easy. So in fact, it is a good point because it is easy to determine. It is not complicated to determine for any kind of system, which is the special form. In this case, this is proportional to omega square. In other cases, generally, it is a power of omega. So it is quite easy to determine which is the characteristic g omega for any kind of system that we are considering. So we determined it for beams, for shells, for a set of oscillators. That depends, of course, how they are connected to the principal oscillator. But in any case, it is a good. It's an easy task to determine what is the omega function.
And for the rocket, it was to complete the system rocket without electricity.
Well, we determine it experimentally.
Yeah, of clear.
Because it is very complicated.
System.
Yeah, but the complete system. Say that I would like to show you just the case that we analyzed. One of the case. So, okay, this is the rocket case. So we have a program in the University of Rome that is called UNISAT. UNISAT means University Satellites. So we have a group of people that generally, that is the name is Gauss group. I don't know why to select a foreign name. But in any case, okay, this is the group that it is a group of astrodynamics of our university. Sorry?
Acronym.
Yeah, it is like the acronym. So we have every 2 years we have a launch of satellites. So you have a rocket. Inside the rocket, you have satellites, as you see here. So there are several floors into the rockets, and then at each floor you have a number of satellites. So the problem is very simple. They want to push the rockets in orbit, then the rocket opens the door, and then you spread out the satellites that go in orbit. Okay? One of them, this one, is.
Trivial question. How they are sure they don't bump?
Oh, they are bolted.
They release one after the other.
Sorry? Yeah.
They release
Yeah.
one after
Yeah.
the other.
Yeah. So can you imagine it is very expensive? Just to give you an idea, in order to put your satellite into the rocket, every 2 years they have to build up a consortium. So there are industries, universities that collect money in order to pay the rocket people in order to organize the launch. So you pay, say, more or less 30,000 euros per kilogram that you want to send in orbit. Okay? So you put your satellite inside, and then you want that your satellite that contains many instruments will arrive safe in orbit. Otherwise, you are spending money to build up it, to launch it to 2,000 per kilogram. And then you can imagine that if the electronic that is inside doesn't work because of the vibration at the switching off of the booster, it's a very delicate problem. Okay, so this is the satellite. So the satellite had some problems because of the vibrations. Then this is the internal structure of the satellite. So we identify the point. So the electronic package was attached to a plate that was inside the satellite. So this was the point of attachment of the electronic package to the plate that is part of the structure of the satellite. So vibrations to the electronic package come exactly from that point. That is the attachment point of the electronic box on the satellite. Okay, so the first step is just to determine some properties of the environment, just looking at the experimental identification of some property of the system that is attached to the box. So we made some preliminary measurement, and so we identified a sharp peak at some frequencies. And of course, this is an experimental result. So you have a very sharp peak in the region that is between 300 Hz and 500 Hz, say, more or less. This is the more clear peak in the frequency response function of your system. So say that this peak in the response is particularly difficult for the electronic package. So suppose that you have at the moment of launch, you can say you have the spectrum of the response of the plate at which your electronic package is attached. What is the real excitation that our box will have? Of course, it depends on the spectrum of the excitation, so the spectrum that is transmitted by the booster. So the booster are more or less random noise, band-limited random noise means pink noise, something like that. Then you, in order to obtain what is the vibrations at that point, you have to multiply the two spectra. Okay? And then, of course, if you have a sharp peak, it results in a very strong component in response of the box. So we use this is the central frequency for our device. It was 438 Hz. Then we want to have an effective bandwidth, so we want to damp the motion of the system within this frequency bandwidth, 375 Hz up to 500 Hz. So we want to damp the system in this region. So we applied the previous theory in order to get the best frequency distributions that we have to include into the box in order to absorb very effectively the energy. And then this distribution that we are talking about is just a distribution of frequency that is represented here. So the one that we were plotting were just academic game, but in this case this is the true distribution that we used. As you see, on the y-axis you have the frequency, and on the x, this is xi, the xi axis is between 0 and 1. And then we can introduce our function that starts at 375 Hertz and if I'm not wrong, is up to 500 Hz. And the distribution, optimal distribution, is like that. 0, 1. Okay? This is the distribution of frequencies. So this is actually the curve that is determined by the best distribution obtained by the variational approach. Then this is the frequency bandwidth. Now, yeah.
If I understood well, that means that your resonators, half of them must be under 400.
Exactly. Mm-hmm. Okay, say that, for example, you want to use 5 resonators. You say 0.2, 0.4, 0.6, 0.8, 1. The frequencies 1, 2, 3, 4, 5, 6. Okay? So you have to realize a cluster of resonators with these frequencies.
So you evaluate the 5 or 10 times the
180. I will show you the design.
180 times.
Yeah. No, 180 resonators. Okay? So this was the analysis, but I would like to show you the design of the resonator that we implement. So this was the result of some patents that we have about that. So we have 3 layers of beams. So this was the selected original design for the system. So I want just to use beams that are attached to a very simple structure. Then you have 3 layers of beams. Okay? This was the original design that we decided to use. The characteristic size for this device are imposed by the design of the satellite. So we have a very narrow space to fit this device. And we have also a maximum limit in the maximum weight of it. It was 140 grams. So it was quite... So we decided to use... I would like to tell you the truth, of course. This was the theory that we developed. Of course, in order to embed this kind of design into the theory, it is not so easy. So you need a sort of transfer of the theory into engineering practice. So you need to, so for example, what is the best selection for the numbers that you have here? Numbers of resonator. What about the gaps between 2? So are all questions that come up when you have to design this kind of system. So what about the lengths of this beam? Of course, we can select the frequencies from this curve. So we selected 180 resonators. They are 60 for each layer. So 30 for each layer and for each side. Then we selected from the frequency distribution, we selected obviously the length using the beam theory, so it is very easy. And then you have a distributions of lengths corresponding to distribution of frequency that you want to realize. These are the design of the system, and this is the final version of the prototype of the resonators that we used on board. So it is an aluminum structure with some alloy for the screws. So this was theoretically the equivalent damping that was determined by the theory that we developed. It means this is the equivalent damping that is a function of the frequency. So this was exactly what we did in order to understand what is the best frequency distribution. And after you determine the frequency distribution, you can determine what is the equivalent damping by our theory that is variable with the frequency. And as you can see, this is an optimal designed damping. That is exactly what cannot be done by the usual system for damping systems. So we have a peak of damping in correspondence of the natural frequency of the system. This is just the damping. So it is the equation of motion can be thought like this. I'm speaking about this coefficient that is frequency dependent, as you see, convolution integral. So you have a peak of. Then I would like to show you what comes up by measurements. So what we made is just to place this device, attach it to an electrodynamic exciter, and then we used an inverse identification problem. So we are exciting a system that we say has this equation. So I know the force that I'm imposing to the system. I know the displacement because I can measure the displacement. I know the mass. I know the spring constant. Identify C, but just on the basis of experiments. And I would like to show what comes up. This is what comes up in terms of identification of the real apparent damping of the device. So as you see, it has a peak, sharp peak, close to the resonant frequency. This is damping. It is not the frequency response, just damping, just this coefficient. As you can see here, there are the effects of the fact that the system is not infinite dimensional, but it's just finite dimensional. So you can see sharp peaks corresponding to the natural frequencies of the system. Nevertheless, using the theory that minimizes the remainder term, you can get and you can say drive the damping to do what you want. This is something that I would like to transmit to you from the first lecture. So this is I was working with this problem not because of the application. So I started to work on this problem in 1999 just because I was working on the subject of entropy in atomic lattices. Somebody told me just to somebody told me that it was not the case to work on a similar subject since I was working in engineering. Several of the initial works I made and initial papers I wrote on the subject, when I went to present my application to become a professor, some wise colleagues suggested me just to erase because they can badly consider it for your evaluation. But after 10 years, from that original ideas, you can come up with some patterns. This can learn something that generally the capability of obtaining new results is really unpredictable related with ideas that you have in completely different areas. I think that the way to try to drive the research, saying that, guy, this is the goal, so this is our initial position, so you have to go straight in this direction, never worked in the past. So the real good point that you generally find when you produce research is not this. So you are moving from this point to this, but actually at a certain point there is something that you discover and the direction is this and the goal is different from the first that was your original goal. So say it is not important that you move from this direction to this direction, having a very sharp railway on which you have to go. No, in my opinion, it's not very important. The very important thing is that you have to move. So you have to change direction, but the very main point is that you have to move. So I was working, and I'm still working on this research, but just because I am interested in the theoretical part that is just behind these things. But at a certain point, there exists the possibility to translate everything for applications, and it is important. But after that, the capability of using this kind of research in order to match some industrial needs.
But why you are, instead of using beams, you don't try to use plates with variable length and thickness?
Okay, we wrote some papers about that. In a sense that using shells with double curvature, you can very easily determine special frequency distributions that can help. And in particular, we wrote a paper about shells that naturally, because of the curvature, have the property to have these inflection points into the frequency distribution. The real point is that if you use shells are very radiating structure in terms of acoustics. So if you take beams, the radiation efficiency in terms of acoustic emission of beams is much less than radiation from plates. So it means that if you realize this kind of system using plates, you have a very strong radiation in terms of acoustics. Maybe this is not the case for these applications because, yeah. But the real point, for example, we are using these kind of concepts in order to design interiors for airplanes, interiors for helicopters. In this case, the problem is a little bit more complicated because, of course, you are trying to reduce vibrations. And what is the reason? Vibrations is make you uncomfortable. But now, if you reduce the vibrations and then you have a tremendous sound, of course, it doesn't worth to work on it. So what I would like to transmit to you is that actually we are doing a good job with damping, but not acting with dissipation. So we are producing and we are pushing the damping to do what we want, but just modifying the elastic properties of another part of the system. And I think this is probably the main point of these lectures. So I can determine a local properties of the damping here, just modifying the elastic property over there.
And in this example, the time T star.
It was one of the concerns. So it has been selected the way that the time it takes the energy for being transmitted back to the master is a time that is sufficient for the beams to actually dissipate the entire amount of energy. So the return time is like this. You have the pulse, then you have something that is like this, and then the energy comes back. But this is true if the system is truly Hamiltonian. Say that in reality they are not in some sense. So there is a sort of dissipation.
There are atomic resonators.
Yeah, exactly. So very small scale. It is Hamiltonian, still Hamiltonian, but at so small scale that we are not interested in describing them, and we use damping, in fact. But this resonance time is important if during this time the energy that is just leaving into the resonator has not time enough in order to be dissipated over there.
And so there is also a true dissipation that helps
Yeah, I don't want to use the term true dissipation, but it's a true dissipation. Okay.
But do you know if somebody started an investigation of how the atomic resonators are distributed in frequency, and if nature has already chosen your optimal?
Okay, so very recently our papers.
We must record this.
No. Our papers were mentioned.
Reputation.
No, well, exactly this work and some previous work about entropy was recently cited in physical journals, in physical review, in order that they recognized that these papers illustrated quite fundamental properties for these resonators that can be applied also to theoretical physics. Now, the problem is that in general in physics they are not interested to redesign the nature of the atoms in order that they can do something for us.
What about true
Distribution. Oh, well, true distribution in physics. Okay, true distribution in physics is like that. It's related to the heat capacity. So you have a finite number of oscillators because atoms are a lot but finite. So if you consider, for example, the capability, so the absorption capability in terms of head capacity of a real body can be investigated just considering them as resonators in a similar manner that you can do that. Then it's very important that, as we found here, the number of resonant frequency for each band is the key parameter. Even in the theory of thermodynamic theory for heat, you have something like that. So what you have is that there is something like this for the number of resonator for each frequency. So initially you have that the number of resonant frequency increases very rapidly. This is because the vibration modes are more dense when you increase the frequency. It is quite obvious, even in structural engineering. One very particular exception is the case of the beam. In the beam, the natural frequencies have a gap that is increasing with the frequency, but it's just the single case in which it happens. In general structures, the number of resonant frequency for each frequency band increases with the frequency, up to a certain limit, of course, because of the finite number of particles. It is sure that if I take a piece of glass or a piece of metal, the number of resonating atoms is finite, even if it is very large. So I have to expect that after the last frequency corresponding to the highest mode of the atomic lattice, you have not any more modes. So you have not any more natural frequencies. So what happens is the critical frequency here, and beyond this limit you have not any more natural frequency. So you have a special distribution like that. This is called, you can imagine that at this frequency you can have something that is a particular effect. because there is a change in the trend. And this is related to the Debye temperature. It's something that is quite investigated in physics. So actually, in physics, they are not very much interested in this part. Say that if you look at the real scale, it's something like that. So generally, the distribution of frequency they take is 1 over omega square, this part. Okay? So this is what nature did for us.
So we are more clever than...
Sometime. Okay, so this is the comparison. This is the device on board. It's mounted on board. And it is bolted at the point of attachment. And this is the comparison of the blue line is the Unisat without the device. This is the response that you have without the device, blue line. And the red curve is after the installation of the device. And then you can see a very remarkable reduction of the vibration level that you have on board. Okay.
The frequencies are breaking brittle materials.
You have to ask to Jill. I don't know about anything about them.
If you place a piezoelectric ceramic actuators there, are they broken by vibrations?
No. But they cannot be used during the switching off of the booster, because any kind of electrical system must be deactivated except the guidance system.
Even if it is a capacitor with low currents?
Yeah. In that case, but just because it is a special application. So there are any kind of device using vibrations that do not need such special requirements. So I can say that more or less that's all for today. Thank you.